Himanshu sir to conduct the session.
Good morning, students.
Good morning, sir.
I'm sharing my screen. If this is visible, then let me know. Visible?
Yes, sir.
Okay. So in the last class, we have discussed about the hybridization. Now we will start about the VSEPR theory, that is valence electron pair repulsion. VSEPR theory. Valence shell electron pair repulsion theory. Okay, the scientist who gave this theory is Sedgwick and Powell. So these are the two scientists who gave this theory. So now tell me what the name suggests. The name suggests that I'm talking about the valence shell. It means outermost shell. Second thing, there are electron pairs. Third thing, we know that if there are electron pairs, negative charge repel each other. So that is called repulsion. So it means if I'm talking about the valence shell, that is outermost shell in which electrons are present which are doing repulsion. So this total theory based on the repulsion between the electrons. Clear? Second thing, you know that if any of the compound is any of the element, for example, A is an element forming compound with B and another B. So it is forming a compound. So it means around this is known as central atom. Around this central atom, we know that there are electrons of B also, electron of A also, electron of B also. So A is surrounded by the number of electrons. And number of electrons, if A is surrounded by number of electrons, it means there is a possibility that electron will do repulsion. Clear? I'm saying that A is surrounded by two atoms, B and B. Let's take one more atom, B. So A is surrounded by the atom, by the electron of B, and itself A also. So if the number of electrons are more, it means the electron will tend to repel each other. Why electron repel? Because they are negatively charged. So it means the electron will repel. So it means there is a repulsion. If there is a repulsion around the central atom, so what is the condition to get the maximum stability? Minimum repulsion or maximum repulsion? Yes, anyone? Condition for maximum stability: minimum repulsion or maximum repulsion?
Maximum, sir.
Pardon?
Maximum, sir.
Maximum repulsion? No. Condition is, see, if one atom is here, one atom is here, and one atom is here, and another atom is here. So I'm making this a sort of drawing that just tell me in which condition this is condition A, this is condition B. In which condition there is maximum repulsion? A or B?
A, sir. B, sir.
A condition. See, A atoms are close to each other. If atoms are close to each other, it means the condition will be maximum repulsion. And if condition will be maximum repulsion, it means low stability. Every element tend to occupy the minimum repulsion. if minimum repulsion will be there, it means what will happen? There is a maximum stability. Every element tend to occupy the minimum repulsion condition, because if minimum repulsion will be there, electrons will be settled and they will get the maximum stability. Okay, so just remember this point: maximum repulsion, low stability; minimum repulsion, max stability. Okay, so this is the thing that you have to remember. Okay, so in VSEPR, the main thing that we have to remember that lone pair and lone pair, lone pair and bond pair. Again, third, bond pair and bond pair. Since all this condition, in all these three conditions, we know that all lone pair, all bond pair, or lone pair, bond pair, they are made up of electrons. So it means there is repulsion. So there is a repulsion. Now tell me which lone pair, lone pair, lone pair, bond pair, bond pair, bond pair. Which one will have maximum repulsion? Lone pair, lone pair, lone pair, bond pair, or bond pair, bond pair?
Lone pair, sir.
Achha, why? Why lone pair, lone pair? If we are saying something, it means there must be a reason. So why lone pair, lone pair? Anyone else? No? Okay. See, in case of lone pair, answer is correct. That lone pair is maximum. But the condition is why lone pair is maximum, just because lone pair is present on the same atom. Lone pair is present on the same atom. For example, I'm taking the water molecule. So it have two lone pair. So it means why it is not straight water molecule. It is sort of this like structure. What is the reason? The reason is what will happen just because the lone pair is present on the same atom, they are close to each other. So they will do repulsion. When they will do repulsion, this lone pair will also repel the bond pair. This lone pair will also repel the bond pair. So there's a bent shape. They bent downward. So it means they were tend to occupy the minimum repulsion. So that if they'll have the minimum repulsion, they will have the maximum stability. So the correct answer is yes. Lone pair have the maximum repulsion, then followed by the lone pair and bond pair, then followed by bond pair and bond pair. Bond pair and bond pair. Clear? This much is clear. Why lone pair is having the maximum repulsion? Lone pair having the maximum repulsion. Just because if anyone asks lone pair, why maximum repulsion? Because they are present on the same atom. Because lone pair are present on the same atom, while the lone pair, bond pair are on the different atoms, so they have maximum distance. So if distance is more between the atoms, it means repulsion will be less. So lone pair are on the same atom, lone pair, bond pair different, bond pair different. So that's why in case of lone pair, there is a maximum repulsion. Clear?
Yes, sir.
Okay. Next thing what you have to remember is that if condition, first condition is if only bond pairs are present. If only bond pairs are present, no lone pair is present. So it means the repulsion will be less. If only bond pair are present, then repulsion will be less, or you can say approximately negligible. Okay, if only bond pair present, then geometry of molecule will be symmetrical. But I'm saying about AB2 type molecule that there is a symmetry. Okay, but if I talk about if lone pair are present with bond pair, if lone pair are present with the bond pair, condition same AB. I'm taking a AB2 type condition, but in AB2 type condition, A is having a lone pair. A is having lone pair. So this is A. A is having one lone pair, and here B and B. What will happen? This lone pair will repel the bond pair. This lone pair will repel the bond pair. There is a distortion in the shape. So it means if lone pair are present with the bond pair, then there is a distortion in the geometry of compound. So you can say that they are not symmetrical if lone pair is present. Clear? 2 points I said. If only bond pair are present, it means there will be no repulsion. So the geometry will be symmetrical. While if there is a presence of lone pair in the compound, at that particular time, lone pair will repel the bond pair, and lone pair bond pair, when there is a repulsion, it means there is a distortion in the shape. There will be a distortion in the shape. Clear?
Yes, sir.
Okay, third condition, if lone pair is 0, can I say that shape of the molecule is equals to the geometry? Just because this one shows the shape, okay? This lone pair one. So I'm saying when lone pair is equals to 0, it means there is no repulsion. It means lone pair and geometry are same. So if you remember, when we were learning about the hybridization, we have learned one thing that, okay, just tell me the shape fast. SP, the shape was
Linear, sir.
linear. Okay, in case of SP2,
Trigonal planar.
Trigonal planar.
trigonal planar. Very good. Okay, SP3,
Tetrahedral.
tetrahedral. Okay, SP3D,
Trigonal bipyramidal, sir.
trigonal bipyramidal. Okay, and SP3D2,
Octahedral.
octahedral. Another name of octahedral. Another name of octahedral is square bipyramidal. Okay, SP3D3, SP3D3, pentagonal bipyramidal. Revise that class. And what is the shape of DSP2? Last hybridization I told. That is square planar. So these were the hybridization, and these were the shape. So we have learned there was no lone pair. But if I'm saying about NH3 have sp3 hybridization. So according to sp3 hybridization, two conditions there: N, H, 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 and N, H, H, and one lone pair. So if I'm considering the lone pair, then the shape will be tetrahedral. Otherwise, if I'm not considering the lone pair, it will be pyramidal. So this is the effect of lone pair. But we have to learn in this VSEPR theory. So in case of VBR theory, what VSEPR theory, okay? VSEPR theory tells about the shape of molecule. It tells about the molecule shape and bond angle. So this is the only work of VSEPR, that it tells about the shape of the molecule and the bond angle. So let's discuss the postulates. What were the postulates given by this VSEPR theory by Sedgwick and Powell? Okay, the first postulate is the shape of molecule. Shape will totally depend upon the number of valence shell electron pairs. What is it? That there only the shape can be determined by the number of valence shell electron pair. Second thing, what VSEPR tells, that valence shell electron pairs repel one another. It means there is a repulsion between the electron pair present in the valence shell. Third thing, what it tells, that electron tend to occupy minimum repulsion. Why minimum repulsion? Why minimum repulsion? I told you earlier. What happened? I think. Yeah.
Stability.
To get stability, yeah. To tend to occupy the minimum distance so that maximum stability can be attained. 2 days holidays were not sufficient, I think. You guys are sleeping. Okay. Fourth point. The valence shell is taken as a sphere. What? That valence shell is taken as sphere in which the electrons are delocalized. Electron pair are localized at maximum distance. See, if maximum distance will be there, it means there will be less repulsion, and less repulsion, it means the maximum stability. So these are the 4 points. Okay, if I talk about the fifth point, that the electron pair in multiple bond are treated as single unit. Electron pair in multiple bond are taken as single electron pair. It means if I'm talking about 2 or 3 electron pair of a double bond or a triple bond, they all are considered as single electron pair. Okay. 6th point about the repulsion order. What was the repulsion order? Lone pair repulsion is more, then lone pair, bond pair, then bond pair. Next and last point is that as repulsive force decreases with increase in bond angle between electron pairs. It means if repulsive force will decrease, when repulsive force will decrease? When there is a less repulsion between the lone pair. So if it is happening, then it means the bond pair will move and bend, you can say. So this was the total thing given by the VSEPR. Now we'll discuss about the shape of molecule. Okay, so just first type, that is AB2L. That is, A is the central atom. A is central atom. Always I'm taking A as central atom. B is bond pair. L represent lone pair. Okay. So first type is AB2L. It means one central atom, two bond pair, and one lone pair is present. C, A, B, and B. Okay. If I talk about the AB2 type, when I'm not considering as lone pair, then it must not be like this. It must be like linear. If lone pair is not considered, it must be linear. But just present because of the presence of lone pair, there is a repulsion between this lone pair and bond pair, lone pair and bond pair. So you can see earlier the bond angle was 180 degree, but now just because of the repulsion, the bond angle is decreased. So this is called distortion is in the shape of distortion in the geometry of molecule. So now see, earlier it was linear, but due to the presence of this lone pair, there is a change in shape, and now the shape is known as V shape or bent shape. Clear? When one central atom, two bond pair, and one lone pair is present, then we use as AB2L, and the shape will be V shaped or bent shape. And examples you can see SO2, O3, SnCl2. These are the example. S is central atom, O is that bond pair atom, bonded atom, and one lone pair present. Okay, second category I'm taking as AB3L. It means, anyone just tell me, how many central atom? One.
One central atom,
And three,
three bond pairs,
Bond pairs.
and one lone pair. Okay. So in this condition, if I go, I told you earlier also that A, B, B, and B. One condition, A, B, B, B with a lone pair. So two conditions is there. When I'm not considering the lone pair, the shape is pyramidal. But just because I'm talking about the VSEPR theory, then the shape is distorted and the bond angle is decreased. So without the lone pair, I'll say the shape is, okay, I'm saying this as shape. This shape is pyramidal, but according to the arrangement of atom. According to the arrangement of atom. I'll share one, 2 pages of this, a table of this, okay? This will be easy for you to remember. So according to this, you can say this some way you can see that this is a tetrahedral sort of shape. So if I consider the lone pair, it was tetrahedral. But just because we don't write the lone pair, so if anyone asks the geometry, you will say tetrahedral. If someone asks the shape, you will say pyramidal. Example I told you, NH3. You can take in place of A, you can use N, and rest you can use H. Next side, AB2L2. It means now the lone pair is increased. So just tell me, if lone pair will increase, the repulsion will increase or not?
Increases.
It will increases. It means now I'm taking two lone pair, two bond pair, and one central atom. So if condition is A, B, 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 okay, sorry, we have two B1, B, and the condition, another condition is, okay, normally if I'll not take lone pair, and other condition is when I'm taking lone pair. So if I'll take lone pair, this will considered under the category of tetrahedral. It means the geometry will be tetrahedral. But if I'll remove this lone pair and I'll not consider this lone pair, it will be a sort of bent shape, or you can say V-shaped. Example, water molecule. Okay, so you can write like this one also. So you can see lone pair, lone pair. I wrote the lone pair in place of lone pair. So this is sort of tetrahedral shape, but we are taking it as V shape. Next type is AB4L. It means one central atom, 4 bond pair, and
lone pair.
1 lone pair.
Oh.
Okay. So if I take this as AB4 type, so A, B, 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 and this is lone pair. See, it can be like this, but just because there is a repulsion, between this lone pair and bond pair. So what will happen? This will repel this bond pair, and this lone pair also repel this bond pair, so they become straight. Okay, so in this condition, this sort of shape, geometry, is known as what? Trigonal bipyramidal. Trigonal bipyramidal. The geometry will be trigonal bipyramidal. But just remove this lone pair and make this diagram, this structure, sorry. This represents something. I think in your childhood you play a game that is seesaw. One will sit this side, one will sit this side, and up, down. I don't know what seesaw in Hindi or any other language. So the shape is seesaw, and the structure you can use here is SF, for example. Okay, so the shape will be seesaw, and geometry will be tetrahedron. Next type is AB3L2. It means 3 lone pair, 3 bond pair and 2 lone pair. 5, total 5 things are there. Okay, A, B, B, B. These are, see again, this is again trigonal bipyramidal.
Bipyramidal.
Yeah, the geometry will be trigonal bipyramidal. But if I talk about the shape, remove the lone pair. Which alphabet it look like?
Lane.
Huh? See, which alphabet is this?
T.
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 So if I remove this lone pair, so it will be sort of this A, B, B, and B. So sort of T is there. So that's why we consider it as a T-shaped. Shape of the molecule is T. in case of AB3L2. Next one. I'm considering AB2L3. Now, bond pair is only 2 and lone pair is now 3. Again, one lone pair, one lone pair, one lone pair. Okay. So, again, if I say the structure is again trigonal bipyramidal.
Bipyramidal.
The geometry will be trigonal bipyramidal. The shape, remove this lone pair. Which shape is this?
Linear.
Linear. Yeah, the shape will be
Linear.
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 Example is XCF2. Xenon fluoride. Next, AB5L. It means 5
Bond pair.
and 1
Lone.
lone pair.
Lone pair.
So A, B, 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 and this B and 1 lone pair. So which geometry?
Octahedral.
Yeah, it will be octahedral. The geometry of the molecule will be octahedral. But if I remove this lone pair, it will be like A, B, 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 and one B is A. See, in the mid, there is a formation of a square, but if I join all this, so it will form a
Pyramid.
pyramid-like structure. So it will be square pyramidal. No bipyramidal, just pyramidal. Just because one pyramid is forming. Okay. Example, you can take BRF5. Next and the last one is AB4L2. It means one central atom, 4 bond pair, 2 lone pair. So in this condition, A, B, 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 one lone pair, another lone pair. Shape or geometry?
Tetrahedral.
Tetrahedral.
No, sir.
Octagonal.
Octahedral, yeah. Octahedral. Okay. The geometry will be octahedral. But just remove this lone pair. Now the shape.
Square.
Yeah, square.
Pyramid.
Planar. There is no pyramid. See, they all are present on the same plane. So they are known as square planar. Example, XCF4. Clear?
Yes, sir.
See, if you are having confusion in the geometry and that shape, do one thing. For example, condition was AB2L. So it was 2 bond pair and 1 lone pair. Total is 3. So the 3, what geometry you were making earlier? In 3, it means sp2. 3 means sp2. For sp2 hybridization, that was trigonal planar structure A, B, B, B. So you can remember like this only. Condition, it totally depends upon you if you want to. For example, AB3L type, it means 3 bond pair, 1 lone pair, any sp3. So in case of sp3, the shape was tetrahedral. This is a geometry, okay? This is all our geometry. So for remembering of geometry, you can use this thing. But in case of lone pair, you cannot. You have to remove the lone pair. You have to remember that if there will be no lone pair, then how many bond pairs are present and how we can tell the shape of the molecule. So this much is clear?
Yes, sir.
Okay. Then let me check the book. Anything else is remaining in this? VS EPR theory. See, there is one shortcut thing also, but I'm not teaching you shortcut right now. I'll tell the shortcut after the completion of the chapter. Some things I'll tell you. Okay. So just tell me, you have learned some things in the this periodic table chapter. What is bond length? What is bond length? Are no one knows bond length. See, if two molecules are bonded together, two molecules of any of the compound is bonded together, just take the average distance between the two nuclei.
Nuclear.
Yeah, this is known as what? Bond length. So just remember, the bond length is inversely proportional to the bond energy. It means if longer bond length is there, the energy will be
Less.
Less.
less. If a smaller bond is there, bond energy will be
Large.
more, yeah, large. So just remember, the bond length is inversely proportional to the bond energy. Okay, what are the factors which affect the bond length and bond energy? That is, first factor is size of atom. See, bond length is inversely proportional to bond energy. We have learned earlier, and that is directly proportional to the size of atom. It means explain this thing. It's quite basic. If the atom size is bigger, if the size of atom is bigger, it means more bond length will be there, and if more bond length will be there, then bond energy will be less. Normal. Okay. Second thing, if bond length is inversely proportional to the bond energy, and it is directly proportional to the bond multiplicity. Wait. Bond energy is directly proportional to the bond multiplicity and inversely proportional to the bond length. It means if there is a shorter bond length and if there is a longer bond, two things are there. If the bond length is short and number of bond will be more. See, as the number of bond increases, bond length will decrease. Remember this thing. If number of bonds, see, bond multiplicity, what means? Does it mean the number of bond will be more? Single bond, double bond, triple bond, so just like this. So if the number of bond will be more, it means number of bond length will be shorter. And just tell me, if bond length is short, then to break that particular bond, you require more energy or less energy?
More energy.
More energy will be there. So it means bond energy will be more. Clear? Two things.
Yes, sir.
Okay. Third one. Percentage of S character. Percentage of S character is directly proportional to the bond energy and inversely proportional to the bond length. See, now tell me basic three hybridization, sp, sp2, sp3. In this condition, 50% S character and 50% P character. In this condition, S character is
75.
S character is
33.33.
3.333.
33.33 and P character is 66.66. It will go on. Okay. In this condition, S character is
25, sir.
25.
25. In this condition, P character is 75. Okay. So if more S character will be there, the bond energy will be more. Why? See, I told you one thing, that if single bond is present, then it will be sp3. Double bond will be present, then sp2 hybridization. Triple bond will be present, then sp hybridization. Okay. So, and earlier I told you one thing, that if the bond will multiply, if there will be bond multiplication, it means double triple bond will be there, the bond energy will be more. Same in this case, if you will see triple bond having sp hybridization. If triple bond is having sp hybridization, the s character is 50%. So if s character will increase, the bond energy will increase, and obviously I told you, when the bond multiply, the bond length will decrease. So bond length will decrease. So if I talk about the maximum bond energy, if I talk about the maximum bond energy, just tell me which will have the maximum bond enthalpy. Okay, bond energy. Okay, I'm making the shape. CH3 single bond, CH3. Okay, then CH3, CH2 double bond, CH2. In these two conditions, just basic example. You don't need to see this triple and the number of hydrogen. Just check about the double or triple bond. So in these two conditions, CH3, CH3 or CH3 double bond, CH2 double bond, CH2. In which condition the percentage of gas character is more?
C. Double bond, sir.
CH3.
CH3.
This one have more S character, no? Just because double bond is there. So if double bond is there, it means 33.33 S character is there. So the percentage of S character is more, the bond energy will be more. So it's a basic thing. I think you have learned one story in your childhood. Generally, that is present in the books and all. That there was a farmer. He have 3 sons. He gave one stick to every person and just break it. So they can easily break, just because it was a single thing. But when he what he did, he just put all the sticks together, and now he said that just break it. No one was able to break. Why? But just because it was a multiplicity of the that stick. So he just want to explain that if you remain together, you will have the strength and all, something like this. The same way you can resemble here. If the bond will be more, it means for breaking every bond or each bond, you require more energy. So same way, if the bond will multiply, it means the more energy will be there, bond length will be shorter, and S character will be more. So just remember these three only. First thing, second thing, and this one is third thing. Any thing what you want to ask? Okay, I'm asking one thing. Question is, CH4 and NH3, they both are sp3 hybridized. Okay, but in case of CH4, the bond angle is 109.28 minutes, while in case of NH3, the bond angle is 107 degree. What is the reason?
Lone pair, sir.
Lone pair repulsion. Okay, clear? Anyone have doubt in VSEPR? Anyone have doubt? Then ask. Otherwise, I'll start a short topic so that I can complete it today. and we have only one main theory is left, that is molecular orbital theory. Okay, and tomorrow we will finish the dipole movement. We'll go for the dipole movement, then drawback of the VPT, that limitation of the VPT, and then we'll go for the molecular orbital theory. So molecular orbital theory take 2 days and the chapter will be done. Okay, then after that I'll give you some sort of questions, you can solve it. Okay, let's start with basic, a new topic, that is hydrogen bond. Probably you know this, hydrogen bonding. Okay, what is hydrogen bonding? No one knows. Okay, so if I talk about the hydrogen bonding, it's an attractive force. It's an attractive force which bind hydrogen of one molecule, with electronegative element, with electronegative atom. Which electronegative element the condition is? Just remember one thing, only fluorine, oxygen and nitrogen of another molecule. So it's a sort of attraction between the hydrogen of one molecule to the electronegative element of another molecule. And that electronegative element must be either fluorine, either oxygen, either nitrogen. So 3 atoms are there, fluorine, oxygen and nitrogen. So you can, what is the cause of formation? What is the cause? What is the reason why there is an attraction? Why there is an attraction? That the responsible force is electrostatic force. Remember electrostatic force when I started this? What was electrostatic force? Again. Electrostatic force. You guys are not revising. Positive charge was attracting the negative. I told you that when the positive charge attracts the negative charge, that force of attraction is known as electrostatic force of attraction. Okay. So just because of presence of electrostatic force of attraction, see, I'm talking about basic example I'm taking of hydrogen bonding, that is HF. Hydrogen and fluorine. They both are, see, in this condition, fluorine is electronegative element. So it will acquire the partial negative character, while the hydrogen will occupy the partial positive character. Imagine another molecule of fluorine is present, HF is present. So what will happen again? Partial positive and partial negative. Another fluorine is present, partial positive and partial negative. Now what will happen? The negative of this will attract the positive of this. Negative of this will attract the positive of this. So there is a sort of attraction between the negative and the positive ion present in the molecule. So that's why I'm saying it as electrostatic force of attraction. So this is a sort of attraction between the hydrogen of one atom, hydrogen of one molecule, to the electronegative element of the another molecule. The HF is a different molecule. So this sort of bonding is known as hydrogen bonding. This sort of bonding is known as what? Hydrogen bonding. And if someone asks the reason behind the hydrogen bonding, the reason is only the electrostatic force of attraction. Just because the positive charge attract each other, that's why we are considering as hydrogen bonding and electrostatic force of attraction. So what are the conditions? What is the conditions for hydrogen bonding? Some conditions are there, and the conditions is, first condition is high electronegative. High electronegativity of atom bonded to hydrogen. See, the other element must have the high electronegativity. Just because if there will be a high electronegativity, then there is a separation of the charges. For example, I was talking about the F. Fluorine is the highest electronegative element, so it will get the partial negative character very easily. It will get the partial negative character very easily. So if it will get the partial negative, hydrogen will get the partial positive. So it means there must be electronegative difference between the hydrogen and the fluorine atom. Second condition, if I say small size of electronegative element. Electronegative element. Why? Smaller size then greater attraction. Smaller size and greater attraction of the bond pair. See, generally, electronegative element has a small size. Why small size? Just because the number of shell was same and the nuclear charge was increasing. If the number of shell remains same and the nuclear charge is continuously increasing, it means the outermost electron is easily holded by the nucleus. So at that particular time, the electronegativity increases. So these are the two conditions we have to remember, that the condition is electronegativity of another bonded atom must be more and size must be small. So two things is types. First type is intermolecular hydrogen bonding. Second type is intramolecular hydrogen bonding. Okay. If I talk about intermolecular and intramolecular. Intramolecular, it means within the same molecule. Within the same molecule. If hydrogen bonding is present, then it is called intramolecular hydrogen bond. But if different molecule, if I'm talking about the different molecule, then it is known as what? Intramolecule. Different molecule. Clear? What is the difference between intra and inter? That if it is present in the different molecule, it means I'm talking about the intermolecular. And if I'm talking about only within the one molecule, then it is known as intramolecular. So example is HF, 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 HF. So the fluorine will attract the hydrogen. This will attract the hydrogen. For showing this hydrogen bonding, we generally use 3 dashes. 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, sort of this. So now I'm giving one example. Second example is orthonitrophenol. Orthonitrophenol. See, this is benzene. Above benzene, if OH is present, we say it as phenol, and nitrogen, one oxygen, double bond O. Now this hydrogen will attract the oxygen. Okay, this is condition 1, this is condition 2. So tell me, which condition 1 is intermolecular or intramolecular?
Intermolecular.
Intermolecular, just because it is present between the different molecule of hydrogen fluoride. While in case of orthonitrophenol, there is a intramolecular, just because it is present within the same molecule. Okay, what about water?
Intermolecular.
Intermolecular, that's HOH, then O, here H, then you can take one more example, O, H, H. So this will attract, so they form a cage-like structure. That's why it is also considered intermolecular hydrogen bonding. Okay, now a basic question and my last question for today. Okay, just tell me, just think quite deeply. In case of inter or in case of intra, which will have more boiling point or melting point? Which will have more boiling point or melting point? Okay, I'll tell you this thing in next class, but tell me for today, I'm giving you one homework. Okay, what is boiling? Question is, what is boiling? I'm not talking about boiling point. I'm not talking about melting point. The question is, what is boiling? I just want to know. Okay, so let's wind up this lecture here, and I'll talk about this horizontal bonding in next class also, and I'll start the remaining portion, the small topics, which is whichever is left in this particular chapter, I'll take tomorrow. Then I'll go for the molecular orbital theory, and the chapter will be done. Okay, maybe within the 2 to 3 days, the chapter will be done. Then I'll start the organic portion. So thank you so much, and now you can join the next class.
Students, please join the next session.